welcome everybody to The Spoken Nerd, the podcast about database technology. I'm your host Connor McDonald, and in this episode we're going back to basics. And the basic element we're talking about the database today is also a silent killer, the one thing that can absolutely cripple your database no matter how much CPU power it's got. So today we're going to talk about parsing. But in order to talk about parsing, we really need to take a step back and really focus this session on CPU. A friend of mine named Kevin once said, everything in database technology is a CPU problem. And in particular, when it comes to the topic of parsing, we'll see that a little bit of parsing can cause a whole lot of CPU headaches. To understand parsing and its relationship to CPU, we need to take a little bit of a trip down memory lane and look a bit at the history of how servers, in particular database servers, have come to be. When I went to university or college, depending on how you name it, I won't share what year that was, I remember we learnt about all the fundamentals of computer technology. I remember an author named Andrew Tenenbaum. That was the nemesis, in my view, in terms of the kind of stuff we had to learn. We learned about NAND gates and transistors and all the various low-level things that made up computers because they were still deemed quite novel. I remember in my C language course, we had to write a disk head seek scheduling algorithm. And the whole time I was writing this project, I can't help thinking, surely this has already been done. But we are where we are. Computers in those days, and this is one of the things we learnt about through our various textbooks, were all based on what we call bus computing. The bus was the fundamental glue that allowed components in the computer to talk to each other. If a CPU wanted to talk to memory or the network or the I/O controller, pretty much anything talking to anything, that was done via what we call the bus. The bus is effectively an appropriate metaphor because it's similar to commuting around a city. If you want to get from point A to point B, then you would jump on the bus. Thus, in this generation of computers, it was the speed of the bus that pretty much defined the speed of your server. If you had a fast bus, then your server could perform well. If your bus was slow, then that might be the limiting factor. In those days, the bus was very rarely the limiting factor because in reality, everything on computers in those days was breathtakingly slow. You might have a bus speed of, say, something like 166 megahertz, but that was never a problem because CPUs used to cap out at 20 or 50 megahertz in those days. I remember my first computer I worked with Oracle was a Sun Spark 20, which I think ran at 60 megahertz because we'd paid for extra CPU power. Perusing back those old textbooks of mine, I used to see the term FSB, front side bus. The front side bus was effectively the CPU's gateway to the outside world, in particular things like memory, the network controller, I/O controller, etc. The backside bus was how the CPU talked to its own level 2 cache. Buses were not a problem because they were faster than the technology that was attached to it. But of course, as we know, CPUs changed over the years. The conversation of my bus runs at 166 megahertz, but that's okay because my CPU runs at 50 megahertz, changed to something like my CPU can run at 1 gigahertz, but that's a problem because my bus is limited at 166 megahertz. The bus became the limiting factor in terms of getting your service to run well. And then AMD came along and pretty much changed the world. They arrived with a processor which had a technology known as hypertransport. Now, for those who are dinosaurs like myself, please don't jump on the comments and flame me. There's all sorts of stories going around about how Silicon Graphics really invented this, or Sequent invented this, or other companies were the pioneers, etc. So who knows who actually owned the original patents? But for me, AMD was the first processor architecture that came across my radar where I saw that the bus was no longer an issue. This processor technology was memory being bolted directly onto the CPU board, therefore a CPU could access its memory incredibly quickly without having to go through any bus whatsoever. That meant incredible CPU to memory access performance. Now, if you've got multiple CPUs in a machine and each one has its own memory bolted onto it, then effectively this means a NUMA style architecture, non-uniform memory access, because accessing some memory, the memory that's bolted onto your own processor, is going to be faster than accessing memory on another CPU's board. Original NUMA systems didn't have such a great reputation because of the huge differences between accessing memory that was local versus accessing memory that was remote. But AMD had also another technology known as hypertransport, which meant that you could do incredibly fast communications between the CPUs, thus achieving a much closer to parity memory performance speed. I remember in those days, there was a dramatic change in the landscape when it came to database benchmarks. We all used to go to those benchmark websites and it would be all huge, massive, monstrous machines from Sun or HP or IBM. And all of a sudden, the performance per CPU suddenly became dominated by machines like Sun Opteron or from Dell or Compaq, and they all had these AMD chips in them. An Oracle database does a lot with memory, and therefore being able to have those CPUs no longer constrained by a front-side bus meant that they were pretty much the machines of choice when it came to running database, in particular running database benchmarks. This, I think, was the beginning of the massive shift from huge boxes that we used to run databases on to smaller boxes, typically running Intel or AMD, and of course the rise and rise of Linux. It wasn't just AMD that jumped on this bandwagon. Intel saw this, and I know some people may say that Intel stole this technology. Not me. I just remember the tension in the marketplace back then. People used to argue over who had the patents for what. But Intel came up with their technology, I think it was called QPI, for Quick Path Interconnect. And as the name suggests, it sounds very similar to hypertransport, the ability to rapidly shift information between CPUs that had their own memory integrated onto the controller. I think that was around about 2007 or so, and people of that generation may remember the term Nehalem, the Nehalem Intel architecture. And as a result, Intel AMD chips were now getting the speeds to match, or even better, the rivals from the huge machine makers of Sun, AIX, etc. Now, as a DBA or developer or just general listener on this podcast, you're probably at this point saying, oh, who cares about all that junk? I didn't come here for a server hardware history lesson. But let me explain why this is important. And I'll do so by saying I actually feel an enormous amount of empathy, almost pity, for the younger generation who missed what I would deem a golden time for IT professionals when we used to have slow servers. Now, this seems strange, but in those times, you could do an application with beautiful code, really efficient, and wonderful database design, and still not be able to meet the performance needs of the business you're building applications for, because the server hardware simply couldn't do the job. You might be thinking, well, why is this a good thing? Because the reality was the converse then came into play. You could do a shoddy design, some crappy code, and when it ran like junk, you could always just wave your hand and say, it's not my fault, it's the problem with the server technology. The advancements in server technology, the introduction of things like hypertransport and QPI and Nehalem and those new architectures meant that that argument has been thrown out the window. Today's servers are simply breathtakingly fast. And that's why I feel for the younger generation, because they can no longer say it's a problem with the server. If the server can't do the workload you are trying to ask of it, then rest assured it's generally a poor application code or poor application design that is the issue. It's no longer the hardware. I do a simple demo at some of my presentations where on my laptop, which is a 2016 model Dell XPS, I can do about 50,000 queries per second against its local database. Now, I did a Google search before I started recording this today. I can get that machine for about $600 refurbished off eBay. So a $600 machine that weighs just over a kilogram can do about 50,000 queries per second. It is insane what you can achieve on modern server technology. So at this point, you're probably going, thank you, Connor, for this podcast on how dinosaurs like yourself got away with application murder back in the day. How does this relate to SQL parsing? Well, hopefully I've established that a modern server is more than capable of running pretty much any workload you could ever ask of it. So when you can't achieve that workload, then rest assured SQL parsing is perhaps the most common cause. To explain why, let's get some common ground first on some terminology. I want to talk about the definition of what I would call a cursor. If you're an application developer, you'll probably be well familiar with the term, but it's a slightly different definition. From a developer perspective, a cursor is probably the kind of thing you would see in your own code. You would declare a cursor, open it, fetch from it, etc. A cursor is, from an application developer's point of view, the concept of retrieving rows from the database. But from the database's perspective, I'd like to adopt a different definition, A cursor, from the database's perspective, is simply a pointer to an area of memory. An application requires the database to do some work. That work will need some memory access. Therefore, we allocate cursors to point to that memory in order to give access to that memory to the code that's about to run. Just like from a developer's perspective, where we would say that a cursor has 3 phases, we would open the cursor, fetch from it, and then close it. We can adopt the same kind of terminology for the database definition of a cursor. Open cursor says, please database, allocate me some memory such that you can do some work. Rather than fetch, I will say process is the second phase, where we will do some work with that memory. We might change some memory, we might read some memory, we might bring stuff into that memory area. And finally, when we close the cursor, that's our application code telling the database, you can have that memory back, we no longer require it. From the database's perspective, everything is a cursor. If you do a query, if you do DDL, if you run a stored procedure, anything that requires memory and therefore work to be done, from a database's point of view, is you dealing with cursors. You can make the argument, well, that almost covers any kind of operation running on a computer. Every operation requires memory access. However, why do we have databases? What is so special about them? It's they support memory access and data access by multiple users, multiple processes, all at the same time. The beauty of databases is that they take care of all the concurrency and consistency issues. They make sure you don't get corruptions, etc. What this, of course, means is that any kind of memory access needs to be controlled. We can't have people changing memory while other people are reading it. Before I talk about how that is done, let's do a quick primer on database memory from an Oracle's perspective. And from what I've read, this is pretty much the same on almost any database platform. Almost all memory inside databases is typically doubly linked lists, because one of the most common things we have to do is walk along various chunks of memory in order to either see data or change data, etc. You think of buffers in the buffer cache, we walk along buffers to find the right information we need, etc. Most memory in an Oracle database system is a doubly linked list, and we need to control access to it because we have multiple users going for memory at the same time. I was about to say the best way to describe this, but maybe best is a too generous a term. A hopefully interesting way I can describe how Oracle controls access to memory is to think about the metaphor of a rock concert. Now, perhaps this will be an inappropriate metaphor given the last 2 years of COVID, none of us have been at any kind of group event anyway, but let's assume that we had rock concerts and we were doing our normal thing. At any large group, one of the most frustrating things is when you need to use the public facilities, like the restrooms. I'm not sure how it is in whatever city you're listening from, but here in Australia, there is never enough restrooms for the size of the crowd at any particular event. Therefore, ultimately, it's a bit of a lottery whether you can actually get into the restroom. But a restroom is a good metaphor for Oracle memory. It's a limited resource. Lots of people are competing for a limited resource, namely memory. A standard toilet looks simple enough, but it's a fairly complicated structure. There's plumbing and all sorts of stuff that needs to go on, and therefore it's a complicated resource. And as you can imagine, if you have a corruption and more than one person is using that single resource at the same time, that's a fairly uncomfortable situation, and some awkward conversations tend to result. Now, how do we avoid that? It's fairly obvious that we don't like those kind of things happening, so when you're getting access to a public restroom at a rock concert, what do? We don't just barge into a cubicle and take our chances. Everyone agrees to a common access mechanism. You go in there and you look at the door, and there is some simple indicator that is controlled by the person inside the cubicle that tells you whether the cubicle is currently in use or not. And if you ask even a non-IT professional, what's the component on the door that they use to make sure that they don't have any awkward conversations in a public restroom? It is, of course, they say, I would use a latch. And that terminology is identical to what we have inside an Oracle database. In an Oracle database, we can assume a doubly linked list of memory is a complicated structure. Lots of people want to get access to it at the same time. So we protect each of those structures with a latch, a small, lightweight piece of memory that can be accessed very, very rapidly, and it's immediately obvious to anyone interrogating it whether the latch is currently held by someone else, just like in a public restroom. So in order to get access to memory inside an Oracle database, the first step you need to do is to be able to get exclusive access to the latch that protects that memory. Once you've got the latch, you have now been granted exclusive use to those resources. You can now read the memory, change the memory, etc. And when you're finished with the memory, you now release your hold on the latch, therefore letting others come and access it. Hopefully you can see that the public restroom metaphor actually holds fairly true here. And just like a public restroom, what happens when two or more people want to get access to the same memory structure? It means someone has to wait. And just like the public restroom, where you see all these awkward looking people loitering around trying to look innocent around the stalls, waiting for their turn to get access, the database adopts a similar strategy. Given the incredible speed of CPUs, if a process tries to acquire a latch and finds that that latch is currently in use by someone else, for that process to relinquish its current hold on the CPU, go to sleep for a little while, and then come back and try again, is equivalent to you finding all the stalls occupied, leaving the rock concert, driving home, jumping on a plane, flying to another country, flying back home again, and then coming back and trying again. Even sleeping for 1/100th of a second is an eternity in modern CPU timescales. Therefore, the database does not do that. The database takes a far more aggressive approach when it comes to trying to get a latch. If I'm a process and I try to acquire a latch by probing that piece of memory and it is already in use by someone, what do? I try again. And if it's still in use, I try again. In fact, I'll try perhaps thousands of times, because while I currently have a slice of the CPU, it makes sense for me to continue pounding away at that latch, because hopefully, memory access being quite fast, someone else will release that latch and I'll get my turn to grab the latch. If after thousands and thousands of attempts, I still can't get the latch, at that point it's probably time for me to give up the CPU to someone else and I will go to sleep for maybe 1/100th of a second. But I'm hoping that while I'm spinning away trying to get that latch, in one of those thousands of attempts that the other person will release their grip. But if I'm trying to acquire a latch, and in doing so, I'm on the CPU aggressively just going as hard as I can at a single piece of memory, that burns a lot of CPU. The moment I have lots of people competing for the same latch and only one person has it, I end up with a situation where lots of CPUs are absolutely going flat out, burning away trying to get to a single piece of memory. What that means as an external observer, for example, you as an administrator, is you'll see that lots of your CPUs on your database server are running incredibly hot, and yet at the same time, nothing seems to be getting done, because latch contention is hurting CPU, it's hurting concurrency, because if one person has the latch, other people can't get it. And let's be honest here, if you are burning CPU in a modern computing server, whether it's on premises or in the cloud, CPU generally equals money. You pay for the number of CPUs you consume on a database server. So if you're burning lots of CPU and getting nothing done, then that's obviously not a very intelligent return on your investment. So from a server CPU point of view, and from a financial point of view, and a getting things done point of view, having lots of memory contention, therefore lots of latch contention in an Oracle database, is perhaps the worst situation to be in. Now let's see what's involved in running a SQL statement, what it takes to parse a SQL statement to run it on the Oracle database. The first phase of any SQL statement being checked is what we call a syntax check. A syntax check is seeing if a SQL statement that you've presented could conceivably be run not just on this database, but any database. For example, if you do select star from employee, but you've spelt from incorrectly, probably the most common typo I do every time I'm typing SQL is I type in FRMO instead of from. That statement fails a syntax check. It will never run on any database, no matter what. Once I've passed the syntax check, then I move on to what we call a semantic check. A semantic check is this SQL is conceivably valid on some database, but is it valid on my database? For example, if I do select star from emp, but I don't have a table called emp, or for example, I don't have privileges on a table called emp, then I can't run that statement on this database. From a syntax point of view, it's perfectly fine, but from a semantic point of view, it is not valid for this particular user on this particular database. Once I've passed that, I move on to perhaps one of the most complicated phases, and that is optimization. Hopefully you've had a listen to the previous podcast episodes where I chatted with Nigel Bayliss, and you've come to an understanding of just how incredibly complicated the optimizer's job is. Therefore, working out the execution plan for a SQL statement is an incredibly complicated thing to do. Once the database has come up with the execution plan, the next phase is what we call row sourcing. And really, that's just a subtle difference to optimization. Optimization is the execution plan. Row sourcing is taking that plan and converting it into the list of, you could think of machine level instructions in order to actually run your query. The execution plan might say, I need to use this index. The row sourcing might say, that means go to these particular segments on disk, read it in this particular way. It's effectively the machine level operations to implement that execution plan. After all of that stuff has been done, now you can actually start running your SQL statement. We get to the execution phase. And if it happens to be a select statement, then the sixth phase might be fetching, returning those rows back to your client program. Thus, before execution, we've got syntax, we've got semantics, we've got optimization, we've got row sourcing. We've got a lot of preliminaries. That's what SQL parsing is. And every single one of those preliminaries means lots and lots of memory access. And lots of memory access means lots of latching. Lots of latching might mean lots of CPU and lots of latch contention. As I said, if you're doing lots of SQL parsing, you're burning lots of CPU and getting nothing done. This is why I called this podcast episode SQL Parsing, the Silent Database Killer. It doesn't matter how fast your CPUs are. It doesn't matter how fast your memory is, because no matter how quick they are, if people are all contending for the same piece of memory, then all those CPUs will be busy achieving very, very little. Having now painted perhaps a gloom and doom picture of SQL parsing, because after all, you're possibly thinking, well, this must be impossible to avoid. If I want to run a SQL statement, I must parse it. Surely, that's the only way. I must ask the database to check this SQL statement so that it can be run. Therefore, the challenge is, how do I avoid parsing? It seems an impossible task. Well, there's two mechanisms in the Oracle database that we use to minimize the amount of parsing. The first occurrence of any SQL statement must always be parsed, but we've got some mechanisms to try and limit more parsing than that. The first one is what we call a library cache. The library cache is simply an area in memory in which we set aside for previously parsed and executed statements. If I do select star from employee, then what will happen is I'll have to parse it if the database has never seen that. However, if I come back at a later time and also run select star from employee, the first parse of that was stored in the library cache. The library cache stores things like the fact that the syntax was okay, the semantics was okay, the information about the optimizer plan, the row source information, etc. Therefore, on my second parse attempt, when I ask the database to run select star from employee, it is found in the library cache, and the database says, cool, I can skip a lot of the steps I would have normally had to do because someone else has paid that price. That's the idea of a library cache, to hopefully get reuse of someone's effort in terms of their initial SQL parsing. Of course, you might be thinking, hold on a second, how many people are just going to be doing select star from employee? That's not a typical SQL query. A SQL query normally is something like with a predicate, select star from employee where employee number equals 1234. In a broad application, how many people will be accessing the same employee from the same table? It seems unlikely. The probability of reuse of SQL statements would seem quite low. This is where the second mechanism comes in, the concept of what we call binding or placeholders. If I run a query, select star from employee where employee number equals 1234, and someone else runs a query, select star from employee where employee equals 5678, yes, they are different queries. We are looking for different rows in the employee table. But assuming a standard primary key, we could argue that those two queries are very nearly the same. They are looking for a single row, for a single employee, for a provided employee number. The optimizer plan for both those queries is likely to be identical. In fact, everything about those queries is identical except for the value of the employee number thereafter. That offers another opportunity in which we could perhaps take more advantage of the library cache. We could ask the database to parse a representative query. We could say select star from employee where the employee number equals some unknown value at this stage. We ask the database, just parse that and put it in the library cache. Now, when someone comes along and provides that query and says, please parse where employee number equals an unknown value, the database says, yes, I've got that in a library cache already. When it comes to the execution phase, the database simply says, yep, I'll need that value now. So I'll pass in employee 1, 2, 3, 4. Someone else will pass in employee 5, 6, 7, 8. But we will both use the same parsed SQL statement in the library cache, the one that actually had a placeholder or bind variable, a simple representative value that would be provided at execution time. That dramatically increases the likelihood of being able to reuse cursors in the library cache. So that's the two mechanisms via which we can reduce parsing. I've done some demonstrations and presentations where that simple difference between having statements that are parsed every single time versus statements that reuse parsing information from the library cache can give you literally perhaps a 1,000-fold improvement in performance. The reason for that is, as we saw, parsing is an incredibly complicated task. Syntax, semantics, optimizer, etc. A lot is going on. With a complicated SQL statement, it is not uncommon to see parse times of up to even a second. That means even with the most incredibly powerful server on the planet, you can run one query per second maximum. That's not fun for anyone. Compare that to the example I gave earlier where my $600 laptop can run 50,000 queries per second. I achieve that by minimizing to as much as possible the amount of parsing that is done. So hopefully that explains the importance of SQL parsing when it comes to the success of your database applications. Any kind of high volume transaction application you're planning on building will live or die on the amount of SQL parsing it does. We have the library cache, we have binding. Those two things are critical to ensure the performance of your applications. And I'll see you on the next episode. Bye for now. Thanks for listening to this podcast. The music credit goes to Zanman from Pixabay Music.